Fast Track. In this lesson, we'll learn about position time graphs, slope, and touch on velocity time graphs. In the previous lesson, we looked at the difference between speed and velocity. When an object moves, the motion can be graphed and the graph can be analyzed. This will often tell us a little bit more about the speed, the velocity, the displacement, or the acceleration of an object. Here's a data generated when a boat travels at a constant velocity. Now, assuming that it has a running start and it goes by a certain marker at a certain speed, at 0 time, as it crosses past the marker, it has gone 0 distance. After 5 seconds, it will have gone 25 meters west, as the graph, as the chart indicates. After 10 seconds, 50 meters. After 15 seconds, it's gone 75 meters. And here's a position time graph of the boat's motion. We need an x and a y axis. On the x-axis, we put time. Time is the, in this case, the manipulated variable. And of course, on the y-axis, we put the position. The position is the responding variable. And we can see that after 5 seconds, 25 meters, 10 seconds, 50, and so on. And when we connect all those lines using a straight line, or all those dots using a straight line, we notice that the slope of the line is uniform. And that means uniform slope will give us uniform velocity. Remember, the y is equal to mx plus b. In this case, our m is a constant. Our slope is a constant. The slope of the position time graph gives you the speed, and uniform slope means uniform velocity. And if you knew what the direction was, then you could substitute displacement for distance instead of, and in this case we do know. Since we know that the direction is west, it's not just the distance that we know, but we also know the displacement. So it's not just the speed that we'll know, but we'll also know the velocity. The method of finding the speed or velocity from a position time graph or a displacement time graph is that we take the slope. The slope of a position time graph gives the speed. This is a very important definition in Physics 20 and in Physics 30 and beyond. The slope of a line is found using 2 ordered pairs, taken from the graph, not from the data table, but from the graph, and using the slope formula to calculate the rise over the run. So I picked 2 points here. At 12 seconds, it was at about 60, and at 4 seconds, it was at about 20. And of course, to take the slope, all right, these are the 2 ordered pairs. To take the slope, you use the slope formula from math, and it's y2 minus y1. All right, the y2 in this case is 60, the x2 is 20, or sorry, the y1 is 20, and the x2 is 12, and the x1 is 4. All right, ordered pairs are written in the form x and y, as you can see from the formula. So my m value, or slope, is 40 meters. All right, 60 minus 20. It traveled 40 meters in what period of time? 8 seconds. And it seems to be traveling at a uniform speed. And so the speed is 5.0 meters per second. Since the slope is 5.0 meters per second, the speed is 5.0 meters per second. And we know that the boat was moving west, so the velocity is 5.0 meters per second west. Now, in this example, the magnitude of the motion is the same as the magnitude of the speed and velocity are the same, but the velocity must also include direction, which would be, in this case, west. we have to understand that the only time the magnitudes are going to be the same is when the object is moving in a straight line. As soon as we bend to the left or the right, then the speed will be greater than the velocity, all right? Because as we change direction, we lose a little bit of the magnitude of the velocity, all right? We'll discuss that a lot more in circular motion when the speed actually may not change at all, but the velocity is changing quite a bit. Now, what we just looked at on the previous slide was a position time graph for a particular type of motion. The motion graph looks differently if we change the components of the y or x axis. So in this particular case, here's a copy of the graph that we just looked at on the previous page, and we have position on the y-axis and time on the x-axis. If we were to change this to a velocity time graph where we put velocity on the y-axis and leave time on the x-axis, notice that the velocity time graph looks quite a bit different. The velocity was 5 meters per second when the boat went by the marker, and it stayed at a consistent 5.0 meters per second. Now, the slope of the position time graph gave a velocity of 5 meters per second west, and that 5 meters per second is constant because the slope of the position time graph is constant. Now, notice here on the right hand side that the slope of a velocity time graph is 0. Now, this is an important revelation, if you like. The reason for this is that the velocity is not changing over time. It's a constant slope on the position time graph, and so there is no acceleration. It turns out that the slope of this velocity time graph actually gives you the acceleration. In this particular case, the slope of the velocity time graph is 0, and that makes sense because the acceleration of this object is 0. It's not accelerating. It's moving at a constant velocity of 5.0. It doesn't speed up, it doesn't slow down. If it were to speed up or slow down, the shape of the velocity time graph would look different. So looking further into velocity time graphs, we have the graph below, which is exactly the same as the one on the previous slide. We've already established that the slope of the graph gives you acceleration. However, if we look at the graph's area under the line, and that means between the red line and the x-axis, we can see that it gives the displacement. After 5 seconds, the shaded area under the graph, all right, or in other words, after 5 seconds, the area under the curve, which is of course rectangular in shape, gives us 5 meters per second times 5 seconds is a displacement of 25 meters. And if we continue along that line for the next 10 seconds from 5 to 15, the area under that curve is of course 5 meters per second times the total area is 15 seconds, all right, from 0 up to 15 would be a total of 75 meters. And of course the area under the curve then of a velocity time graph is displacement. Now we call it a curve. A curve is really a mathematical term meaning any line on a graph, whether it's a straight line or a curvy line. In this particular case it is a straight line, but we still call it, mathematically, we call it a curve. And when they say under the curve, they mean between the line itself and the x-axis. Now, you can actually have a negative displacement, and we may look at some of those in examples a little bit later on. If you had, of course, a distance time graph, or sorry, if you had a speed time graph, then instead of getting the velocity, you would get the speed. Or sorry, instead of getting the displacement, you would get the distance. All right, just like it says there. All right, so another important idea, of course, as we mentioned earlier, is that the slope of a velocity time graph gives you the acceleration. The graph below is a velocity time graph for an object that is accelerating uniformly. The velocity is increasing over time. All right? At the beginning of the run, the velocity is 0. As you can see, at time 0, velocity is 0. Now, at time 5, the velocity is a little bit higher. It might be 3 or 4. At 10 seconds, it might be 6 or 8. At 15 seconds, it might be closer to 12 or so. And so, at any point along this graph, we can find the slope. The velocity is increasing over time, and notice that the slope of the line would give us a positive acceleration. Now, we haven't put the numbers down for this, but if you were to grab numbers from this graph, you could substitute them into this formula, and you would get the actual acceleration. I'm just showing you the units here. The units give you acceleration because you're dividing meters per second by seconds. That gives us a meter per second squared. And later on in this course, we'll define acceleration in algebraic terms. But from the graph, you can see that you get the unit meter per second squared, which is the proper unit for acceleration. And it says, note that the units of acceleration from the graph are in meters per second or meters per second squared. And as I said, we'll discuss that very soon in another lesson. Now, the displacement, remember from the previous slide, the displacement is the area under the curve. So if, for example, we wanted to find the displacement after 10 seconds, we would have to construct a triangle under the curve or under the line at that particular point, 10 seconds. So at 10 seconds, we would draw a line straight up. Now notice the area under the curve in this case is not rectangular as it was when we had uniform velocity. Here, because we have acceleration, the slope is changing, or the slope is greater than 0, and we end up with a triangular shape under the curve. So we need the formula for the area of a triangle, which is 1/2 base times height, or 1/2 AB, and 1/2, that doesn't have any units, but of course the time, the seconds, if we call A time and B velocity, seconds times meters per second, the seconds cancel and we get meters. And of course, in order to calculate the displacement, you would construct a triangle under the curve and you would get the units meters, which would be good. Now, if we substituted numbers in there, then we would get the proper mathematical answer to this particular problem. What is the displacement of this particular object after 10 seconds? And just a very important summary of these findings, the slope of a position time graph gives you the velocity, all right? Or if you don't have direction, it will give you the speed. The slope of a velocity time graph gives you the acceleration, all right? And of course, the area under the curve of a velocity time graph is the displacement. Now, you will use these ideas quite a bit. I would say the first one, the slope of a position time graph, is certainly used the most. But the other two will come in handy quite a bit. And I would say you really need to practice this stuff. And you will be given some opportunities to do that from your WebCT course. And that's the end of this lesson on motion graphs.